So this is a story about doing quantum simulations using large-scale arrays of quantum dots. As Shudo said, I'm from the University of New South Wales. No one ever knows where New South Wales is. So usually I just include this picture here, and then people automatically know where it is. So it's in Australia. And the work I'm going to tell you about is we're very fortunate to have great collaborations with Cambridge, with Bochum, and actually ETH Zurich, and it's been funded by the Australian Research Council. So within my group, we've got kind of three main project areas. We work on whole spin qubits in silicon, particularly, and that's a lot of fun, where you can take a single hole and manipulate its spin state and do that coherently and do 1 qubit gates, 2 qubit gates, entanglement, all of that nice stuff. An awful lot of engineering, but also some very nice physics when you tie it down to holes. And what's really nice is this involves industry collaboration with IMEC and Dirac. So that's very nice. Another area we work on is how electricity actually moves in clean materials. And it turns out that the approach that we teach undergraduates is incomplete, and there are corrections to that. And these corrections can actually be very large. And this is when electricity flows like water. At high school, we teach everyone that electricity is like water. It turns out it actually is. And the equations that govern how water flow, which is Navier-Stokes, actually can govern how electricity flows in clean materials. And it turns out to be a very useful probe of a whole bunch of fundamental physics. So that's another project we've got going. But today, what I wanted to talk about more is the work that has been primarily led by Daisy Wang and Oleg Klochan on making synthetic quantum matter using arrays of large-scale quantum dots. So, of course, these are the people who actually do the work. This is a slightly old now photo of some of the group members. The people responsible for this work are Daisy Wang, who's a very, very talented experimentalist, and Oleg Klochan, whose labs the work were done in. And I just stand and sort of admire what they do. We have wonderful theorists, particularly Oleg Sushkov at the University of New South Wales and his collaborators, who explain to us what it is that we have been doing. And then none of this is possible without the high-quality crystals that make all of this fundamental science possible. So crystal growth is absolutely everything. And we're very grateful to Dave Ritchie's group at the University of Cambridge, Andreas Wieck's group at Ruhr Universität Bochum, and Werner Wegscheider's group in Switzerland for material. So what I'm going to talk about is why do we want to simulate things at a quantum level, a new approach to doing quantum simulation, and then I'm going to show you some results, how we can create artificial matter with designer band structures. We can turn electrons into holes. We can change the mass of electrons. And then finally, if we make the mass heavy enough, we can actually get some very interesting correlated physics. So the first story, why do we even need to have quantum simulators? And this is a piece of ceramic material. You can make it very easily just by grinding up some materials and heating them in an oven, forms of ceramic. For this material, it turns out we know the precise crystal structure. It has 7 atoms in the unit cell. We know the type and exact position of every atom in the unit cell. So it should be possible just feed these atoms, the positions of their atoms, into a computer and calculate all of its electrical and magnetic properties. And yet, when you do a measurement of its electrical and magnetic properties, this material superconducts. And that's unexpected. We still don't understand why it superconducts, even though this material has been around for nearly half a century. We don't understand not only the superconducting bit. If you go above the transition temperature, so this is a plot of the material property, the type of electrical conduction as a function of how doped it is on the x-axis and the temperature on the y-axis. Even if you go above the superconductor in green, go upstairs, there is this thing called a strange metal. Now what that means is it conducts, and just like dark matter is a phrase used to describe we don't know what it is, or dark energy, we don't know what it is. The strange metal means it's some sort of a metal, we don't understand what kind of a metal this is. So how is it that only 7 atoms in a unit cell is not possible to calculate? And of course, that is the joy of quantum mechanics. So for a long time, there have been suggestions for more than 20 years that if you wanted to simulate these systems that the properties are emergent because of strong correlations between the electrons in the material, maybe you could use a quantum system, a controlled quantum system, to simulate that complicated real-world quantum system. And now this has been going on for 20 years, initially pioneered by ion traps and optical lattices, where you trap single ions and single atoms with lasers, Rydberg tweezers, more recently with superconducting devices, and I would argue now semiconducting devices off the side here. And so this is a major research field across platforms, because you could then start to simulate some of these complicated materials that we don't understand. So there are lots of different approaches. That's what's nice about quantum simulation. It spans many areas of physics. We have atoms and ions in vacuum held there by lasers. The other approach is to use individually controlled quantum dots. So for example, similar to the quantum dots I was showing you where we have silicon, we take individual quantum dots here, and so this is an example from Delft, and these are the quantum dots, and we can control the number of electrons on each of those quantum dots and the couplings between them, and so this is a way to start building up an artificial matter. You can make larger arrays of quantum dots, and this is work that goes back to the 1990s, where instead of being able to control each dot individually, you just have an ensemble and you try and make sure that each dot is identical, and this work is still continuing. And then there's another approach, which is this Moiré-van der Waals materials, where you take a sheet of graphene, as shown here. One takes a second sheet of graphene and just sort of slides it on top of the first one, and then you twist it. And as you put it on top and start to twist it, you start to form these periodic lattice with the Moiré pattern. And these twisted materials have been really interesting. They've shown phase diagrams as a function of doping and temperature that does resemble what is seen in these high temperature superconductors. So this is now a very active field of work, originally pioneered by Pablo Jarolo Herrero, and now many others across the world, looking at these materials that show metal, Mott insulators, strange metals, superconducting domes, and so on. So what's the difference between all these different methods, and what's the similarities? And really, when we teach undergraduates, it's easy to see how they relate. When we teach undergraduates, we teach them 2 different approaches to understanding the properties of solids. One is, let's start from something we understand, which is atoms, and then look at how the atoms interact as we put more than one atom together and the wave functions start to overlap. And this is the tight binding model. So if you take the energy levels in a lithium atom, you've got your 1s, 2s, 2p, and then you have this one lone electron in the 3s band, and that's why it's a metal. And if we put another lithium atom close to it, this 3s level starts to split as we reduce the separation between the 2 atoms into bonding and anti-bonding states, and then the 2 electrons will form into this lowest band. If you keep adding not just 2 atoms, but 3 atoms, 4 atoms, 5 atoms, you end up with a continuum of allowed energy levels at this separation, and that band is half filled, and a half filled band is a metal. So this tight binding approach works very well for insulators and semiconductors, but it's a little bit difficult to do with pen and paper. The other approach we teach undergraduates, and this approach is very much what you do with quantum dots, where you have individual quantum dots, and then you change the coupling between the quantum dots, and so that's changing the effective separation between the atoms, and so you can simulate condensed matter by making arrays of large numbers of quantum dots. The other approach we teach undergraduates is to start with a free electron. We understand how electrons behave in free space, so let's take an electron in free space, and then to that electron in free space we add this potential here shown in green, So we add a periodic, say, positive potential, which represents the positively charged ionic cores, and then we have a traveling wave of an electron. And if you calculate the energy as a function of momentum, for an electron in free space, it's just a parabola. This periodic array of atoms causes an opening, an anti-crossing of these two levels, and there's an opening here where there are no allowed energies, and this is the forbidden energy gap. So it's very similar to the picture that's drawn up from tight binding, but you're just starting instead with a free electron and then adding a periodic potential to it and scattering off that potential. And so this approach is very good for describing metals and their Fermi surfaces and semiconductors. But they're both two approaches to describing the same thing. What are the properties of electrons in a periodic lattice? And this second approach, this free electron approach in a periodic lattice, is perhaps how one might describe electrons in Moiré graphene, because electrons in graphene behave very much as if they're massless Dirac fermions in vacuum, and then when you apply the periodic potential, you start to create flat bands and magnetic states and superconductors. So those are the two approaches, and you can, of course, mirror those two approaches in how you do your quantum simulation. One approach is to take an array of quantum dots, control the number of electrons in each quantum dot and the coupling between them. This works very well, but it's limited to a small number of sites, because for each quantum dot you need at least 2 control signals, maybe 3. You need connectivity to all the gate electrodes, so it gets very difficult to make more than a small number of quantum dots, although there are significant advances in the last few months in this area. The other approach is to take large numbers of sites and say, okay, I'm going to give up on having the individual control, but instead I gain a large number of sites. Of course, you want to make sure that the sites are all identical, so disorder is an issue, and this is sort of similar to the occupancy problem that happens in cold atoms. So you kind of, at the moment, you've got a choice. Do I work with a small number of quantum dots where I've got good control, but difficult to simulate a large crystal? Or do I start with a large number of systems where I don't have individual control, but unfortunately now disorder becomes an issue? Now, for magic and graphene, this Moiré system, this actually hasn't been a problem so far. It has exhibited very interesting physics and phase diagrams showing superconductivity, strange metal, and so on, and this has been a great success. But perhaps what's not so widely appreciated is that it is almost impossible using this, taking 2 sheets of graphene, putting them together, and then twisting one with respect to the other. It's almost impossible to make the same sample twice. One time you might get a twist angle of 1.08 degrees, another time you get a twist angle of 1.16 degrees. So this is not the best way to do reproducible physics. And even in one sample, you can end up with different domains where the twist angle is varying between one part of the sample and another part of the sample. And so there are opportunities to improve reproducibility and angle control. There are opportunities to better control the superlattice potential. And of course, this Moiré system, because you start with 2 triangular lattices and you put the 2 triangular lattices on top of each other, the resulting lattice can only be triangular. And it might be interesting to study a lattice that's not triangular, such as the lattice in the perovskites. So the question is, can we have a system that's both tunable and can simulate large crystals? And that would, of course, be semiconductors. Semiconductors are tunable, and we know how to pattern these into nanostructures. And so people have tried for many decades to make artificial crystals out of semiconductors. Using electron beam lithography, you can pattern an artificial lattice onto a semiconductor. You can then measure the current flowing through the semiconductor, and you can see features associated with that artificial lattice. But the problem is, in pretty much 30 years of study, the lattice potential has always been weak. It's never been strong enough to create a band structure. When attempts have been made to create a very strong modulation, it's also introduced strong disorder or a lack of tunability, and so that has limited studies to date. So what I want to show you now is a new approach to doing this, and how we can use a very flexible approach to create new band structures. So we're going to use a new approach to an old technique. We're going to take the cleanest electrons in solid state that you can have, and the cleanest material that is known is gallium arsenide. So we're going to take a crystal containing gallium arsenide two-dimensional electron system, shown here in red, and then we're going to put a periodic lattice on it. So there's our two-dimensional electron gaps, and to put a periodic lattice, we put on top of it this metal gate electrode that's got holes patterned into it. And that will define our lattice. Then we put a dielectric on top of that, and on top of the dielectric we put another electrode, and this electrode, most of the electric field from that electrode terminates on the pattern gate. Some of it comes through the holes in the pattern gate, and so if I put a repulsive potential on that electrode, I can control the potential. So the pattern gate controls the number of electrons per lattice site, and the top gate controls the strength of the modulation that I'm going to apply to my free electrons. And so when I make that top gate very negative, I copy the lattice potential into the two-dimensional electron system, and whatever the lattice shape is gets copied into the 2D electrons. Because the lattice is defined by electron beam lithography, we can make a variety of different lattice shapes. So the example I just showed you was this honeycomb lattice. But just by changing the electron beam lithography, we can have a triangular lattice, a square lattice, a Kagome lattice, or a lead lattice. All of these are possible to make. What I just want to show you today is the results that just come out of the simplest possible lattice, the triangular lattice. So this is the lattice we'll be studying. It's got a lattice period of about 100 nanometers. So how does this approach compare to what other people have been doing, and why do we think it might be interesting? Well, what matters really is, if I create a lattice, do the electrons sense that lattice, or do they sense disorder and are unaware of the lattice? So the way we characterize this is what is the lattice constant, and what is the length, the disorder scattering length. If the disorder scattering length is small compared to the lattice constant, so the scattering length we can parameterize through the mobility, then you're in this region down here, and this is really a kind of a classical limit. So for gallium arsenide systems, pretty much all work has been done in the rather disordered limit, where the electrons don't really notice the lattice that strongly. You can etch gallium arsenide, you can etch graphene. All of these studies are done in this disordered limit. In contrast, the work I'm going to show you today is done in this limit where we maintain very low disorder, and so the scattering length is much longer than the lattice period, and so we can define a true artificial lattice. So the game is to try and get into this top left corner where you've got a small lattice constant and small and high mobility or low disorder. Of course, you also want to be able to not just create a lattice, you want to be able to tune it somehow. So what you might want to be able to tune is shown here is on the x-axis how strong the modulation you're applying is, and on the y-axis how many bands you can fill in your artificial band structure. So for moire graphene, the modulation strength is about 4 times the Fermi energy, and you can tune it through 1 or 2 bands. For these etched gallium arsenide samples, you can get to a slightly stronger modulation strength, but the tunability is still quite limited. For graphene on patterned substrates, you can't really get to strong modulation strengths. And then for what I'm going to show you now, we can really cover a huge number of accessible bands, and we can go from switching the modulation off to having very strong electrostatic modulation. So that's how we want to create a new Fermi surface. How am I going to prove to you that I've really created synthetic quantum matter? I've created a crystal that doesn't have the properties of the host crystal, but has completely different properties. So if I tell you I've made a new crystal, you'll say, well, show me the band structure. Show me, if you've created a new crystal, that you've created band gaps. Show me, if you've created an artificial band structure, that you've got electrons and holes. And maybe that the mass of the carriers in that crystal are different than the mass in the host crystal. So that's what I would like to show next. So how do you measure the band structure? How do we even know if there's going to be a band structure there to measure? For my triangular lattice, I'm going to apply some periodic potential. This is for the triangular lattice, this is the periodic potential where G1, G2, and G3 are the reciprocal lattice vectors. and r is the position within the xy plane of the lattice. So the strength of my potential, the peak-to-peak amplitude for this potential, is 9 times W, where W is it's proportional to the gate voltages that I can control. So that's the height of the periodic potential that I'm applying here. The other thing that matters is what is the typical Fermi energy of the carriers? What is the typical carrier energy? And for electrons in gallium arsenide, that's typically of order 2 to 3 millielectron volts. So that gives me my natural energy scale, 2 to 3 millielectron volts, and I want to know how big is the peak-to-peak potential compared to 2 to 3 millielectron volts. So if the peak-to-peak potential is 0, then the electrons in gallium arsenide just feel like they're moving in free space or moving in an ordinary gallium arsenide crystal, and E versus momentum, here's energy on the y-axis, momentum on the x-axis, that's just a parabola. So I just have this parabolic band structure here, and that's repeated but periodically, but of course since the potential is 0, there's no anti-crossings, so I just have purely parabolic potential. So now let me turn up the modulation that I'm applying. So when the peak-to-peak potential is of order the Fermi energy, then that parabola that I just showed you here, you see it starts to open up little anti-crossings. You can see one of the anti-crossings there. You can see here's the other anti-crossing. But still, if you look at this band structure, at no point do you see a band gap. There are always available states. So we need to make the modulation stronger. So I turn up the strength of the modulation. Now the peak-to-peak modulation is bigger than the Fermi energy. It's about 3 times bigger than the Fermi energy. And my parabolic band, you can kind of see there's a little bit left of it. But now really it's changed quite a bit. And I've opened up a small band gap here. So if I turn up the modulation even stronger, so now the peak-to-peak modulation is much bigger than the Fermi energy. It's an order of magnitude larger than the Fermi energy. Then you see my band structure is completely changed. There's no evidence of the parabolic bands, and instead what I have downstairs is a Dirac band structure and upstairs a Kagome band structure. And so the moral of this is, if you want to see band structure, you have to apply very strong potential periodic modulation, or in the language of quantum dots, the tunneling between quantum dots should not be too strong. So with a large peak-to-peak potential, we end up with this band structure. However, creating a large potential modulation on the electrons in a two-dimensional electron gas is not easy. In the same way, it's not easy to get a last-minute flight to India. You require that the disorder be very low, otherwise the electrons don't know that they're in a periodic potential. But also, the two-dimensional electron system has to be very close to the gate that's creating this periodic potential. In fact, it has to be much closer than the lattice spacing. So if your lattice spacing is about 100 nanometers, the distance to the gate shouldn't be much more than 30 nanometers. Otherwise, your potential just gets completely blurred out and you don't really notice the potential modulation at all. So we need to have strong modulation, and we need very low disorder. So to get very low disorder, we've spent quite some time optimizing the crystal growth along with our colleagues in Cambridge, Bochum, and Switzerland. And what this is a plot of is the mobility as a function of carrier density for 2 different gallium arsenide wafers at different depths from the surface. And if you look at these numbers, they're a bit difficult to see, but you can see here at a depth of nearly 40 nanometers, the peak mobility is about 2.5 million, which is not particularly high for gallium arsenide. Peak mobilities of 25 million are common in gallium arsenide. So we've sacrificed mobility to bring the two-dimensional electron system as close as possible to the surface of the wafer. And if we go even shallower, the mobility gets even lower. So you might say, well, you've started with a clean system and you've made it dirty. But what I've done is I've got it now very close to the surface, so I can create a strong potential modulation, and still my mean free path is much, much longer than my lattice constant. My lattice constant is 100 nanometers. My mean free path is between 5,000 and 25,000 nanometers. So the disorder is low enough that I should be able to see band structure effects. The other thing you have to take care of is that the array that you're putting down should be perfectly periodic. So if you're talking to a theorist, they say, well, here is the potential modulation that you're going to create with your gates. It's perfectly periodic. The dashed line is where the Fermi energy is, so there's this very strong modulation. And if I calculate in the 2D xy plane what the potential is, it shows this honeycomb triangular lattice. As soon as you put a little bit of disorder in, and it really doesn't have to be very much disorder, then the height of the potential is not uniform. And that's like creating a solid. Instead of creating, say, a solid out of carbon, you're mixing a bunch of different elements. You may have the correct lattice constant, but if the elements are wrong, then you won't end up with a band structure. And what this corresponds to is the disorder they simulated here was just varying the size of the holes by 5% randomly from one site to another site. And that is enough. The size of the holes in the gate, in the metal gate electrode, that 5% variation is enough to make it impossible to see band structure. So we also had to optimize our lithography, and we spent some years doing that. And Daisy Wang really did a fantastic job. And now we're able to make these lattices, triangular lattices, periods between 80 and 120 nanometers. And you can see that everything's pretty much identical. And this can be done over very large areas. And now it's possible to make the lattice on a high quality two-dimensional electron system. And therefore we can do full transport measurements, the resistivity and the Hall resistance of the electrons in this artificial lattice. So what should we expect to see? At low numbers of electrons, we have graphene-like bands where the bands are parabolic at low energy, and then there's this linear crossing at the K point. And so that's my graphene-like bands. And then upstairs at higher energies or more filling, when I put more and more electrons into the lattice, I end up with this Kagome-like band structure with a flat band here, and then again second Dirac points upstairs. There are the first and second Dirac points, and then of course there are also Van Hove singularities, which we'll describe in a moment here and here. So that's the band structure we expect to see. What effect should that have? Well, if I just look at what's happening down in the graphene-like bands, then what I expect to see is at low energies, I have a parabolic dispersion. So the electrons, the excitations here look like electrons. So if I start with a Fermi surface and I add a few more electrons, that Fermi surface gets bigger, so these will behave as electrons. If I increase the filling in this band a little bit more, I now start to fill these states. And that corresponds to this circle having grown large enough that it's touching the edge of the Brillouin zone created by my artificial lattice. And now if I add one or two more carriers, the Fermi surface actually shrinks. And so if the Fermi surface shrinks with energy, with the increasing occupation, those are holes. If I keep filling the bands, I completely fill that first Brillouin zone. And now I start to fill again the next bands. And so I have some carriers here. I increase the number of carriers. And now my Fermi surface has got bigger. And so those are electron-like. And then if I keep going upstairs, eventually these edges merge together and I get a Fermi circle. And if I increase the density, that Fermi circle shrinks. So those are holes. So that's the sequence of carrier types I expect as I fill these lowest two bands. Electron to hole to electron to hole, associated with the graphene bands and the Van Hove singularities in the graphene bands. So that's what we're going to look for, is a carrier type change from electrons to holes to electrons to holes. How do you tell what the carrier type is? If we can identify the electron-hole transitions, that will identify the positions of these Van Hove singularities in the direct point. So now let me get to the measurements. What do we actually measure? In the experiment, what we do is we take our lattice, this is a 100 nanometer lattice at 1.5 Kelvin, we cool it, we increase the carrier density on the y-axis, the x-axis is the magnetic field, and the z-axis, the color, is the Hall voltage. Positive Hall voltage is blue, negative Hall voltage is red. It's perhaps a bit easier if I just take a line cut at a low density, and at a low density you can see that the Hall voltage decreases with magnetic field. It's got a negative slope, so these are electrons. If I increase the carrier density just a little bit, you see that around zero magnetic field I actually end up with a positive slope of the Hall voltage. So those are holes. If I increase the carrier density again, the Hall voltage around zero magnetic field changes sign once more. So those are electrons. And if I increase the carrier density a little bit further, the Hall voltage changes sign again, and I go back to holes. So since it's the slope of the Hall voltage that matters, I change my color map to show not what the Hall voltage is, but the slope of the Hall voltage. And then you can see those four transitions from electron to hole to electron to hole as blue, red, blue, red. So that's what happens as we increase the carrier density. If I compare that with the calculated band structure, we just argued that for these graphene-like bands, I should get electron-hole, electron-hole. So what we measured agrees reasonably well with the expectations we have. Once we go higher in energy, the bands all start to overlap, and you can't really resolve discrete bands, and so you lose this electron-hole behavior. So that's all agreeing quite well. Is there any additional evidence I could show you to suggest that we've made a new band structure? Well, if I look here, this should be the first Dirac point, just here. And I've got the Van Hove singularities above and below it. So if I take the resistance and I plot the resistance here as a function of carrier density, as you reduce the carrier density, the resistance goes up. That's what you expect. But there is a peak exactly where the first Dirac point is. And so that's the equivalent of the peak at the charge neutrality point in graphene due to the density of states vanishing. So at this point here, if you calculate where the electrons are sitting in this lattice, the electrons end up sitting in the minima in the potential, effectively on this array of quantum dots, and the number of lattice sites is about 5,000 in these particular measurements. Now, with mesoscopic physics, it's always important to say, well, as Shudo mentioned, there are lots of experiments that don't work. How do we know this is not just one of your non-working experiments that you're selling us snake oil? And so the data I showed you was from this wafer. It's 37 nanometers deep. It's got an electron mobility of 600,000, 120 nanometer period. And this is the Hall voltage as a function of magnetic field, showing that periodic reversal. We've actually done measurements on multiple wafers. Here's another wafer. It's a completely different wafer. It's got a totally different electron mobility. The lattice constant we've also changed. The size of the device is also changed by a factor of 2. Yet these two pictures look remarkably similar. And if you take the data on the right and just scale it for the fact that the lattice constant is different, so the magnetic field per unit lattice is going to be different. So you scale the effective magnetic field to the lattice constant, then those two data sets pretty much sit right on top of each other. So now we can make lattices of the same constant that behave identically, or we can make different lattice constants that scale on top of each other. We can use different wafers. We always get reproducible results, and that's really very nice and something quite new. Is there any other evidence that we've got a strong lattice? Well, if electrons are living in this artificial lattice, then if I thread one flux quantum per lattice cell, gauge invariance says that everything must be the same as if I hadn't no magnetic field at all. So every time I thread one flux quantum through the lattice, the properties should return to what they were before I applied the magnetic field. So you should end up with periodic oscillations either in the resistance or in the Hall voltage as a function of the number of flux quanta per unit cell. This has been known since the 1960s. It's called Zach oscillations. It's magnetic breakdown of crystal structure. It's somewhat similar to the Hofstadter butterfly, but most measurements of the Hofstadter butterfly are fractional filling. Here we're talking about integer filling. So instead of putting one flux per 5 lattice sites or one flux per 7 lattice sites, we're talking about putting 1 or 2 or 3 fluxes per lattice site. For comparison, in our experiments, we went up to, the data I'm showing here goes from -2 to +2 Tesla. This would be equivalent from going up to 320,000 Tesla in graphene or 100 Tesla in magic angle bilayer graphene. Obviously, those magnetic fields are not achievable in the laboratory, but for us, 2 Tesla is highly achievable. To show you that it's really periodic in the lattice, in the magnetic flux per unit cell, this is a plot of the derivative of the Hall voltage, so the Hall slope, as a function on the y-axis of the carrier density, and the x-axis the flux per unit cell. And you can see that if I go to this point here and then move 1 flux per unit cell, I go back to red. If I move another flux per unit cell, I go back to red. If I use one more flux per unit cell, I go back to red. So it's periodic in flux per unit cell. And then if I start at low densities and take a line cut, that's what's plotted on the bottom. If I then increase the carrier density, you can see these periodic oscillations. The Hall voltage moves to higher magnetic field for the same Hall voltage, but these oscillations retain their periodicity of 1 flux per unit cell. So these are Zach oscillations, confirming that the electrons are moving between sites in this artificial lattice, and the periodicity of these oscillations is completely consistent with the physically defined lattice constant of 100 nanometers. So the X periodicity gives us the number of electrons per band. The Y periodicity gives us the number of flux per lattice. So we can measure exactly how much we have to change the gate voltage by to move from one band up to the next band, up to the next band, and so on. So this spacing is the number of electrons per band, and this spacing on the horizontal axis is what the area of the lattice is. Okay, so how am I doing for time? Okay, then, yeah, 5 minutes, right. Okay, so in the last few minutes, let me show you some results now that are not something that can be calculated, but something that is somewhat unexpected. So we take the same device, we make the potential a little bit stronger, so we've got an even stronger lattice, and now what I want to show you is what the resistance is as a function of magnetic field on the x-axis, and the y-axis is the number of electrons, or the filling per unit cell. And so we're going to start at low number of electrons, and then go up to higher and higher number of electrons. So what you would expect is as you increase the number of electrons, the resistance should go down. So just keep an eye on what's happening at 0 magnetic field as I increase the number of electrons. As I increase the number of electrons, you see the resistance suddenly shoot up, and then it comes back down again. This is sort of unusual for a system that you would say is disorder, because if it was purely disorder, then when you reduce the number of electrons, the resistance should go up, but it wouldn't come down again. Whereas here, if I start up here, I have low resistance, I go down in the number of electrons, I get to high resistance, and then I go down again and I get to low resistance. Moreover, I think as you can see here, I have the same periodicity in the flux per unit cell as I did before, and that indicates whatever is causing this enormous peak in the resistance knows about the artificial lattice. So let's zoom in on just that big resistance peak. So this is just a close in here as a function of magnetic field and carrier density. Red is high resistance, blue is low resistance. As I increase the number of electrons, you see the resistance go up and then come down. The width of this resistance peak, interestingly, is exactly equal to the distance from one band to the other band. So this resistance peak occupies a complete artificial band. It's killed with increasing and decreasing density, and this resistance peak has the same periodicity as the lattice. Because it has this resistance peak is exactly one band wide, that suggests it's not from a band gap, but it's actually from one full band of carriers. And if you calculate what the on-site energy is compared to the hopping, it's actually of order 50. So this means that in this band, we're very much in the strong correlation limit, not the free electron limit. So what's happening in this band? Well, this band corresponds to the, this is the corresponding, we know where we are because if we can count how many bands we've filled, and this resistance peak is occurring when we're in this flat band region here in the Kagome-like portion of the lattice. And in this region, for these electrons in the Kagome band, these three upper ones, what you see is that the electrons now sit on a lattice, this Kagome lattice, where you have these little triangles periodically arranged. So in that Kagome lattice, we expect to see strong correlations because the band is very flat, so we've quenched the kinetic energy. And that is exactly where we see this big resistance peak that is periodic in flux per unit cell. And if you cool down now to lower temperatures, that resistance peak becomes enormous. It's several mega ohms, but we can make it much larger than that. And the width of that resistance peak exactly matches the full band. So this seems to be some sort of correlated insulator. If you apply a very small magnetic field, 0.1 Tesla, that correlated insulator, that resistance peak is dramatically suppressed. It was 2 mega ohms, it now goes down to about 200 kilo ohms, so it's suppressed by an order of magnitude just by 0.1 Tesla. But if you zoom in, it's actually got quite a similar shape to what it had before. And there's this huge peak in resistance always right in the middle of that, where that flat band would be. We've done temperature dependence measurements to say, okay, well, if it's, what could this, could it be a band gap effect, a trivial band gap, or is it some strongly correlated insulator? The interesting thing is that when we apply the magnetic field, we apparently kill the insulator, and yet when we do thermal activation measurements, the band gap, the thermal activation hardly seems to change. We end up with a gap of 1 to 2 Kelvin, even if we change the magnetic field by 1 Tesla, whereas 0.1 Tesla is enough to kill the insulator in the resistance. So the measurements of the activation gap don't seem to be consistent with destroying the insulator. So what is this correlated insulator? Well, we spent some time thinking about it and thinking, well, what exactly is happening when we've half-filled this band? So this is my Kagome lattice. There is 1 electron per unit cell. So I put 1 electron in my unit cell. And then here are all the other electrons in the lattice, each on 1 electron per unit cell. But the cool thing about the Kagome lattice is that I have these empty sites here at half filling of that flat band or 1/3 filling of the total Kagome lattice. I have all of these empty sites the electron could sit on. So it's 1/3 filling of the Kagome crystal. And now let's look why that's so cool for the Kagome crystal and what's special about that compared to other lattices. So I could equally well translate that electron. I could hop to the next site in the triangular, in this little triangles, and I would still have 1/3 filling. And I could also hop diagonally down and again have 1/3 filling. In fact, all of these 3 positions are 1/3 filling of the lattice. So what the electron will want to do is, if they are all equivalent positions, it will try to delocalize across all 3 of these lattice sites. That will reduce its kinetic energy. If the electron delocalizes, then that creates a circulating current. And if I have a circulating current, that generates a large magnetic moment. And so this thing is called a loop current Wigner insulator. It's a model proposed by Chandravarma for the cuprates. Each of these sites generates a local magnetic moment, and that local magnetic moment is rather large. It's of order 10 Bohr magnetons, because it's essentially an orbital magnetic moment. And so I've got these orbital magnetic moments in a periodic array. So you would imagine that they should be ferromagnetic. Actually, at our temperatures, they're orbitally paramagnetic. The ferromagnetic transition temperature is a few millikelvin, so we can't access that. So we have this orbital paramagnet. We apply an external magnetic field. We align all the spins, and the effect of that is to reduce the magnetic disorder. For electrons to conduct, an electron, say on this site, must hop through here, but it can't do that because that site is full, so it has to excite above some energy gap and then travel through. If it's traveling through this lattice of randomly oriented magnetic orbital moments, then that creates magnetic fluctuations. You get strong scattering and a high resistance. You apply the perpendicular magnetic field, you align the magnetic moments, you suppress the scattering, the magnetic scattering, and that causes an increased conductivity, but importantly, no change in the energy gap. So the story is that you can have a huge magnetic response of the resistance without changing the thermal activation. And so that model is consistent with what we observe in the data, not surprisingly, because we derived the model to explain the data, where we see that the resistance is strongly suppressed by the magnetic field, but the activation gap hardly changes. So we think this is a very interesting way to study strongly correlated systems, where we've got now really nice local control of the band filling and the interaction between the on-site intersite interactions. So in summary, what I've shown you is an artificial crystal with designer band structure. We can tune the Fermi energy and the potential over many bands. We've turned electrons into holes. We've changed the electron mass from 0 at the Dirac point to almost infinite, where we have the flat band. There's been a transition from a Dirac to a Kagome lattice. And lastly, we've got evidence of a non-trivial insulator, which is reported in this paper in Nature Physics. And I think in future, it will be very interesting now, having developed this platform, to look at different lattice geometries and also different materials. We used gallium arsenide because it's what we're familiar with, but there's plenty of other materials in which we could create low disorder lattices. And so with that, I'd like to thank you for your attention and to thank all of my colleagues and co-workers.
Thank you, Alex, for a really exciting and fresh off the lab data, I believe. So we have time for a few questions.
I'm sorry, I should also just acknowledge the chairman and say that the technology that led to this work was in no small part due to his work in accumulation mode gallium arsenide devices, and I'm sure he recognizes many of the challenges we went through to get these devices working.
Let's have a few questions from the audience. Yes. Hello. Yeah.
Alex, it's a very, very exciting talk. I got a chance to revisit my Condensed Matter 101, and I have a couple of questions. Let me ask these questions together so that I can answer it together. So you made a statement somewhere in the middle that the tunnel rate between these quantum dots should be low. And I'm trying to understand that. For example, if you are trying to simulate a semi-metal or metal, I would want my electrons to be delocalized. In that respect, should the tunnel rate be high, or you are trying to simulate an insulator? That is number one. question. Second thing is, how many of these quantum dots you need to get a realistic picture of bulk solid? How many you need? You told you have some 5,000 quantum dots. What would be the minimum number? And one more question I have is, did you try or see any signatures of block oscillations in your solid?
So, okay, those are excellent questions. Let me do them in reverse order. We have not yet looked for block oscillations, but you're absolutely right. That would be something very interesting to see, and that's something we should do. So, yes, thank you for that. And then the other question was about basically the strength of the U over T. And so, okay, so if the intersite hopping is too strong, well, let me put it this way. If there is no hopping between the quantum dots, you don't really form an artificial band structure at any accessible temperature, right? So whatever's happening with U and T, they should be larger than your accessible temperature, and they should be larger than your disorder. So they should be the relevant energy scales. Ideally, you want to make sure that both U and T are larger than 1 millielectron volt. 0.1 millielectron volt. They should be bigger than about 1 Kelvin. Otherwise, disorder and finite temperature effects will kill everything, and you won't see anything. So T should be the hopping should be large enough to allow you to do that. It's very easy to get large U upon T just by setting T to what you think is 0, but then you've just got an array of essentially weakly interacting systems. You can say U on T is very large, but that's only because you've made T much smaller than the disorder energy or the thermal energy, and so you're not actually getting to large U on T. That's perhaps what I meant to say. Does that clarify that?
And the number, how small you can, yeah.
That's a really good question. How small can you make the lattice and still form a well-defined band structure? We have gone, I think the smallest lattices we've made are about 20 by 50 unit cells, and we still see good Hall transport and rho XX. So I would say that you would probably want at least 10 by 10 lattice sites, but that's just, a guess. If you've only got one lattice site, clearly you don't have band structure. Maybe if you've got 3 by 3 lattice sites, you're beginning to get band structure. My feeling is you would want to have at least an order of magnitude, so you'd want about 10 lattice sites by 10 lattice sites. That's just very much. We haven't sort of done experiments to go to the small lattice limit, because really we want to compare with these calculations are done for an infinite array of lattices, so we want to be able to compare to that. Things will get slightly complicated if we have to do finite size effects as well as other things to contend with.
Hi Alex, this is Prashant. Yeah, thanks for a very exciting talk. So my question is about the second half of your talk about the Kagome, this loop current Wigner crystal story. So you mentioned that the orbital magnetic moments are quite large, 10 Bohr magnetons roughly. So it should be very easy to magnetize all the orbital magnetic moments using the magnetic field. So I imagine that once you apply a small amount of magnetic field, there should be, beyond that, if I apply even stronger magnetic field, the physical properties must not change significantly because you have magnetized all of them. So have you seen what happens to this resistance when you go beyond 0.1 Tesla? Does it stop changing, or does it still keep decreasing beyond that?
So what we do indeed see is exactly what you've described. Sorry, I don't have a good cut as a function of magnetic field, but red is 1 mega ohm resistance, white is half a mega ohm, and blue is 0.1 mega ohms. What you see is that right at zero magnetic field, you've got this large insulating state, and then it doesn't really change much once you go above about 0.1 Tesla. It just stays white all the way.
I see. And is 0.1 Tesla roughly the right order of magnitude based on the Zeeman energy versus Zeeman energy of the orbital magnetic moments and the kinetic energy?
Well, Oh, that's okay. So this is what was this. You're quite correct. This is what we call the Zeeman effect. Is actually the anomalous Zeeman effect, and this is the orbital Zeeman effect. Yes. So it's a little bit difficult to get an accurate estimate, but it's order of magnitude correct, 100 millitesla to polarize the orbital moments. We haven't done fully detailed calculations. It would be interesting to do fully detailed finite temperature calculations in the presence of small amounts of disorder. But that's quite a non-trivial calculation. So the issue is that we estimate that the paramagnetic transition temperature is a few millikelvin, so we're sort of in a high temperature limit, and then what is the magnetic field necessary to fully spin polarize these electrons?
Okay. Yeah, thank you.
Hi Alex, yeah, really great talk. Just a quick question. So once you make one of your devices, the control over U over T you have is unidirectional, right? Like if you put more U, the T will go down. So if you want to change this, you need to make new devices. Is this correct? Or
let me think. That's a good question, and I don't know the obvious answer to that. I think we have some limited. Essentially, there are three variables. There's the on-site Coulomb energy, there's U, there's T, and there's the chemical potential. And we only have 2 gate electrodes, so we can really only independently control 2 of those things. So we can control the chemical potential with the pattern gate, which also affects the intersite hopping as well through self-consistent Poisson-Schrödinger physics. And we can control the strength of the modulation potential, which is essentially changing both U and T. So we don't have you're right, we don't have full independent control of all 3 things. To change that, we would have to change, the easiest way to do it would be to change the lattice constant a bit.
yeah, okay, yeah, thanks.
Hi Alex, this is Shuddho here, and thank you for a wonderful talk. Just in the interest of time, I'm not going to ask the technical questions I had, but just quickly wanted to say that the person who was introducing you was Kanti, actually, Kanti Mohan Dasgupta.
Yes, sorry.
So you might have seen him on the screen. I just wanted to quickly say that it was him.
No, I saw him wandering past. As soon as I saw him wandering past, I thought I recognized Kanti. Yes, what I should have said is that Kanti was the one really who enabled us to do these low disorder gallium arsenide structures. He wisely gave up on this and moved on to more productive things, and I stayed because I couldn't think of anything smarter to do, doing this for a few more years.
Thank you, Alex, for that. It's always the chairman's job to thank the speaker. I think it's a rare privilege to have the speaker thank the chairman, so I don't know how to reciprocate that. Let's thank Alex for a wonderful talk.
Thank you.